All right, so how can we tell if a molecule is chiral? All right, let's do that. A couple things to look for. Two things we're going to look for. We're going to look for a plane of symmetry. So a plane of symmetry divides a molecule or object into two equal halves that are mirror images of each other. An object that has a plane of symmetry is superimposable on its mirror image and is achiral. Chiral molecule does not have a plane of symmetry. All right, so here's butane. And it's drawn in the anti-conformation. If we rotated butane around this way, this would be the, we can call this the front view. And if you see, there is a plane of symmetry. So what that would be like is that, I'm going to put it as a dotted line. You're probably not going to be able to see it, so go ahead and do that on yours, and it should be able to show up a little better for you. So what we can do is we have a plane of symmetry. So it's like we sliced this molecule in half. And that half is the exact mirror reflection of that half. Everybody see that? And we actually sliced these atoms in half, and that's OK when we're looking for planes of symmetry. So this side is exactly the same as that side. So we would say that this molecule has a plane of symmetry. What does the plane of symmetry look like? Let's draw it right here. So this is in the eclipsed conformation. So the anti-conformation has one plane of symmetry. This is the eclipsed conformation, and it actually has two. So this would be the eclipsed conformation. So here's a dotted line here, and this has a plane of symmetry that goes like this. So you can imagine, you know, when you butterfly a steak, you go along the length of it, and you slice it that way. That's what we did right here. We're just laying this on its side. So we can slice that molecule this way, and the top half will exactly match the bottom half. We can also, there's also a plane of symmetry here because this side of the molecule is the exact mirror reflection of that side. So that plane would look something like this, where we're cutting it in half this way. So we can go this way, and we can also go that way. So those two planes are perpendicular to each other. I tried to show it as best as I can. Now, if we make a really simple change here, and we take one of the hydrogens of butane, one of the hydrogens that's in the middle, and we change it to a chlorine. So that would be this right here. So I'll draw your attention to that. We no longer have a plane of symmetry. So this is 2-chlorobutane. There's 2-chlorobutane. And so I've tried the anti-conformation. I've tried the eclipsed conformation. And all these planes of symmetry are gone because if we try to have a plane that just kind of goes right through your page, right straight down, this chlorine would have to match another chlorine on that side, and it doesn't. Okay, so there's no plane of symmetry that way. There's no plane of symmetry this way because this chlorine doesn't match that hydrogen. We would have to make that hydrogen a chlorine also. And we can't do that, so because it's a completely different molecule. So no planes of symmetry. So therefore, the molecule is chiral. So that's one way we can look for chirality. We can also look for chirality by looking for a tetrahedral atom with 4 different substituents. A tetrahedral atom that has bonded to 4 different substituents constitutes a stereocenter, or a chiral center, or a stereogenic center, or you will also see chirality center. All of those terms are interchangeable. So if there's one chiral center only, so this compound, for example, has one chiral center because we have a carbon, and we usually signify it with an asterisk. That carbon has 4 different groups attached to it. So if there's one chiral center only, there is no plane of symmetry. And the molecule is chiral. So I've signified the chiral center, the stereo center, the stereogenic center, the chirality center, all of those words. That's the chiral center. Or stereo center. Those are the two terms that I will use. So notice up here, we said this molecule is chiral, and we noticed it was chiral because we couldn't find a plane of symmetry. But if you look at this carbon right here, this carbon is attached to a chlorine, a hydrogen, an ethyl. This whole group is an ethyl, and this is a methyl. It's attached to 4 different substituents, right? So that's a chiral center. So this one's also a chiral center. All right, so if we have one chiral center, the molecule's automatically chiral. Automatically chiral, okay? If, however, we have a compound where any 2 substituents are the same, so if we have any 2 substituents the same on a tetrahedral carbon, it doesn't matter what they are. If any 2 substituents are the same, on a tetrahedral carbon, that carbon is achiral. All right, so going back to this compound right here, if this hydrogen was also changed to a chlorine, we no longer have a chiral center and the molecule's achiral. So the reason this is chiral is because here's our front view of this molecule. That's the chlorine, right? And that's why we don't have a plane of symmetry if that becomes chlorine. But if this side also became a chlorine at the same time, now we do have a plane of symmetry and it's achiral. So look for stereocenters, carbons, tetrahedral carbons with 4 different groups attached. If you have one of those in the molecule, the molecule's automatically chiral. If you have, and let's draw 3D structures for this. And we'll just use ET for our ethyl. Save us a little time here. That would be 1 enantiomer of 2-butanol. This would be the other enantiomer of 2-butanol. This one on the left is minus 2-butanol. We'll talk about what that minus means coming up in just a few minutes. Minus 2-butanol, this is plus 2-butanol. To change from one enantiomer of 2-butanol to the other, you actually have to physically remove 2 bonds from your model and switch them. Okay, so that's the difference there. If you have 2 or more chiral centers, the molecules can be chiral or achiral. We'll see examples of that. can be chiral or achiral. More at the end of the chapter, or just more later in the chapter. So if you have a tetrahedral carbon with 4 different substituents and there's only one of those in the molecule, your molecule is chiral. If you have more than one tetrahedral carbon with 4 different substituents, the molecule can be chiral or achiral, and again, we're going to talk about that coming up. Questions so far? Anybody? All right, let's look at the let's look at the Elmo. All right, so things that are chiral and things that are not chiral. Okay, so here's our plane of symmetry in the middle there. Okay, so I have this pumpkin I still have left over from Halloween. So is that chiral? Well, we can slice it in half, but the right half and the left half do not exactly line up, so that pumpkin is chiral. You didn't even know that about pumpkins. Okay? You could probably make a plastic one that was exactly the same on both sides. It would be achiral. Here's our 2 molecules. We have this is our alkene, so if you can see it that way, there's our alkene, and there's the other alkene. They're mirror images of each other, right? But I can take this molecule right here and I can flip it over, and all the bonds exactly line up. Okay, so that means that this molecule is achiral, because this mirror image is superimposable. All right, these guys, let me see. I just grabbed these, so I don't know if they're. Let's see, I got to switch to these groups here. Let's see if I did that right. So definitely, if you have not opened your models up, now see what I did is I switched them and I put them right back in the same spot that they already were. So, okay. You'll find yourself doing the same thing. All right, I want these to be mirror images of each other. Okay, so now they're mirror images of each other. Everybody see that? Okay, they're mirror images, right? Now let's see if they're superimposable. So what I'm going to do is I'm going to flip this over, and I'm going to try to line up bonds. I can line up 2 of the bonds. I can line up the green and the orange. I cannot, but if I do that, the blue and the yellow are not lined up. They're switched. I could line up the blue and the yellow. There's no trickery here. I can line up the blue and the yellow. If I line up the blue and the yellow, the orange and the green don't line up. So these are mirror images. Let's put them back as mirror images. They're mirror images that are not superimposable. So they're chiral. Each one is chiral. In order for me to change this molecule to this one, I have to switch 2 groups. This time I'm going to pay more attention. I have to take 2 bonds out and switch them. All right, and if I do that, everything's superimposable, see? But you know what? Now that I've done that, they're not mirror images anymore. Okay, so enantiomers are really unique. These guys are not mirror images anymore because I've taken 2 bonds and switched them. All right, something else I want to show you here. This is cyclohexane. Now, your models that you have, if you have the green ones, they make better chairs than this one because these are a little bit too flexible. So now I'm trying to line that up. It's kind of shadowy, isn't it? Can you see that? We can't make that shadow go away. Oh well. What's better? Anyway, okay, so what are you thinking? Is that chiral or achiral? All right, well I have the red is an oxygen, and the oxygen is bonded to a hydrogen. And if I put it in that conformation with that hydroxyl over to the right, that hydrogen to the right, then it doesn't have a plane of symmetry. But if I rotate it like this, I can slice that, right? So I'm going to slice that bond, I'm going to slice that bond, I'm going to slice that bond. That side is the exact reflection of the other side. So it is a chiral or achiral? It's achiral. All you need to do is find one orientation where there's a plane of symmetry. You can always rotate things so there's no plane of symmetry, but you just have to find one that has a plane of symmetry, and that automatically means that the molecule is achiral. Okay? And the other thing is that here's our hydroxyl. This carbon right here, what is it bonded to? We're going to look for a tetrahedral carbon. That tetrahedral carbon certainly has it has two substituents that are the same. So how would we do that? That carbon's bonded to a hydrogen that's popping up. It's bonded to a hydroxyl. The other two groups are the two sides of the ring. If we trace the ring around to the left, that's one substituent. And if we trace the ring around that's to the right, if we trace it around to the left, that's another substituent. And that substituent, even though it's the same ring, they count as two substituents, are identical. We encounter the same groups as we're going away. So that carbon right here is a stereocenter, and it is the only stereocenter in the molecule. This carbon right here is not a stereocenter, it has two hydrogens. This carbon right here, 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 and here is not a stereocenter, it has two hydrogens. So we said that if we have one stereocenter, the molecule is chiral. Well, this doesn't have any stereocenters. Okay, so it's achiral. So those are our two tricks to look for things. Questions, anybody? All right, let me do something here. I'm going to make one more. I just thought of this off the top of my head. Let's look at this molecule right here. All right. Well, certainly it doesn't look like it has a plane of symmetry, right? Because we have green this way, yellow this way. And do we have stereocenters? How many stereocenters do we have? We have two stereocenters. This carbon right here. Let me use this. This carbon right here is bonded to a yellow, a green, a blue, and this, I don't know, methyl-y kind of looking thing. Same thing over here. This carbon here is bonded to green, blue, yellow, and this other group right over here. Now, if I switch, I'm going to switch the green and the yellow. So we have two stereocenters, right? I'm going to switch the green and yellow on this side. Do we still have two stereocenters? Yeah, we do. We actually do. Each carbon is bonded to 4 different things. But now, do you see we have a plane of symmetry? So it has 2 stereocenters, but it's achiral. So we said if there's 1 stereocenter, it's automatically chiral. If there's 2, it can be chiral or achiral. I first showed you chiral. This is achiral. Okay? So that's just a little visual before we start moving on to talk more in depth. Any questions? All right. Where? Right here. Yes.
Can you show that the butane with the flames intersecting the model?
I don't have butane, but you can come to my office and we'll look at it. Okay? I don't have butane with me. All right. Okay. So let's talk about drawing enantiomers. We use 3D dash wedge to draw enantiomers. So here's a sample question here. Draw the enantiomers of the following compound using 3D formulas. So 3D meaning dash and wedge. So first we want to find any stereocenters. Draw in the tetrahedral skeleton. And fill in substituents. And definitely you want to take a look at the handout and drawing stereoisomers. It's under the practice link of our website. Okay, ways to draw stereoisomers in ways that are not going to be that are not correct. So I'm going to draw in the skeleton here. I'm just going to do it, and you'll find that you'll favor one way or another based on whether you're right or left-handed. But I'm going to draw my carbon skeleton like this. So I draw 2 bonds in the plane of the paper, and I'm trying to attempt to do 109.5. And then the other 2, the dash and the wedge are close together. Now that's not what the bond angle is. Remember, one of these is coming up and one of these is coming down. So we put those 2 together on the opposite side. So and now I'm just going to distribute the substituents here. So this carbon right here is a hydrogen. I'll put the hydrogen here. I could put it wherever I want, really. The methyl, it has also attached to a methyl, so we'll use CH3 for that. It's attached to a bromine. I'll put bromine here. And then we also have a CH2OH group, so that would be CH2OH here. So that's one enantiomer. And now I'm going to draw the mirror image, because it says to draw both enantiomers. There's actually 2 ways to do this. You can draw the mirror image. And so that's what I'll do first. Some people have trouble with this. So I'll show you another way to do it. So that's the mirror image. So draw a mirror image. Or, when we had our models over there, we said that if we want to change from one enantiomer to the other, we have to physically remove 2 bonds and switch them. So that's another way to draw an enantiomer. Switch any 2 groups. Any 2 groups. All right, so I'm going to redraw it the way I originally had it. There's my skeleton. Which groups do you want to switch?
Bromine and CH2O.
Bromine and the CH2OH. Okay, we'll put bromine here. And CH2OH here. We're going to leave the hydrogen and the methyl exactly where they are. So we're giving you 2 ways to do this. To draw the enantiomer, you can draw the mirror image, or switch 2 groups. Don't draw the mirror image and switch 2 groups, or you're going to be right back to the original enantiomer. So on your own, here's what I recommend that you do. Make this model. Make this model. And you'll see that there are enantiomers of each other. But also make this the way it's shown, and make this, and you will see that those are identical. That you make the model, one enantiomer will be superimposable on the other. We're not ready yet. We've got 2 more minutes. So this is the other enantiomer.